So as Randy said, I'd like to tell you some of the work we've done with our customers and how we are looking at some of the problems that actual customers have through the quantum lens, but also try to give them some value today by finding alternate ways of solving these. You probably have seen this slide before a few times. These are the pillars of AWS. On the left-hand side, we have Amazon Braket, our service where we host quantum hardware. On the right-hand side, we have the Center for Quantum Technologies. As a matter of fact, it's actually two centers. We have a Center for Quantum Computing and a Center for Quantum Networking. And in the center, which will be the focus of this presentation, is the Quantum Solutions Lab, where we engage actively with our customers and try to find applications for quantum machines or quantum-type solutions for different problems that actually are really difficult for our customers to solve. So what is our mission? Our mission is to basically prepare every customer for a quantum future. In other words, assess their use cases and see if a quantum device will be able to tackle them down the road. But ideally also deliver value today by raising the bar for quantum machines using combinations of machine learning, high-performance computing, novel algorithm development, and of course also quantum technologies. So we firmly believe that the most scalable way to get meaningful results out of quantum machines down the road will be hybrid workloads, and this is really what we're trying to experiment with. Now, how does this Quantum Solution Lab engage? At Amazon, we have this peculiar behavior that we don't just build a hammer and look for nails. We usually go to our customers and say, where does it hurt? What is the problem that you cannot solve, that you're trying to solve here and that you're struggling with? And then based on that, we advise the customer what the best way forward is to find a solution. So what we typically do, if you look at the center arrow here, we usually start with a target use case. I don't know, let's pick something random, portfolio optimization. Then we talk with the customer how they could solve this on a quantum machine, do a small-scale POC. But in parallel, we leverage alternate technologies like machine learning, for example, nature-inspired algorithms, high-performance computing, to actually solve these at scale. And so every time that we engage with a customer, we try to go in this dual track that on one hand gives the customer a POC that will help them assess what a quantum machine of a particular size, type, capability will be able to do in the future versus the state-of-the-art solution that we have today that often combines these technologies. Now, since I don't have very much time in this presentation, I just thought I'll show you some of the cool things that we've been working on. And those of you who have heard me talk in the last year have probably seen a subset of these. Usually what we like to start with is what I call the incomplete menu of use cases. And what you can see here is a very incomplete laundry list of some of the problems that customers have and that they bring to us with the hope that we can solve this on a quantum machine. Needless to say, very often the answer is not anytime soon, but maybe in the future. And so you can see there is a color coding here. Red is a traditional HPC, high-performance computing workload. Blue is machine learning, and we have that expertise in-house at AWS. Orange is something that can run eventually on a quantum machine, hopefully at scale. And green is either a traditional classical operations research type solution or a solution where we develop a new algorithm, a new approach, and I'll show you an example of that later, to tackle this particular industry use case. As you can see, there are certain areas where quantum is very prominent, for example, in chemistry and simulations, as you probably would not be surprised. But there's other areas like logistic, transportation, and routing where it's not present. And the reason is very simple. The overhead that we see when we're trying to solve a routing problem can be enormous. Converting a capacitated vehicle routing problem into a QUBO, which is the language that a quantum machine understands, requires such a large overhead that at some point the practicality of the solution does not help you anymore. And so we have stopped really trying to tackle these unless we come up with something clever, a completely new way of encoding these problems. And this is, of course, still active research. But you can see that in manufacturing, there's a couple of use cases that can be massaged relatively straightforwardly to run on a quantum backend, like job shop scheduling and factory line optimization. But already problems like robot motion planning become very much intractable. They're a similar case as capacitated vehicle routing. Chemistry, as I said before, there's many ways of solving problems in chemistry, battery design, molecular similarity, catalyst discovery, et cetera, and typically we try to leverage combinations of these technologies, augment, for example, a quantum device with traditional machine learning, such that we can solve problems in molecules at scale. Logistics and transportation, the bread and butter of Amazon. We have developed some interesting solutions there and work closely with our supply chain optimization team. And then finally, finance, which I say currently the most signals in the quantum field, portfolio optimization, risk analysis, options pricing, and fraud detection. All use cases that we've looked at, that we have dove into in detail, and where I'll show you a couple of use cases in the next slides. So let me show you now 4 or 5, I don't remember exactly how many I put in there, use cases that we have been looking at with our customers. The first one is something really cool that we did with BMW, and this is robot motion planning. What you can see in the top left are the robots in BMW's plant actually spraying PVC sealant onto a car body. And when you think about this problem, it's nothing else than a cousin of a traveling salesperson problem, except that the individual stops or nodes, or the cities, if you want to call it that way, are composite nodes. There's information about the type of nozzle, the configuration of the nozzle, the spraying direction. So if you think about it, the amount of effort needed to encode this in a QUBO is enormous. Okay? So post-embedding to a sparse topology of a machine, a typical production problem would require about 10 to the 11 qubits. And as you can imagine, this is not going to happen anytime soon. So how do we solve this? Well, first we did a quantum computing POC. We leveraged D-Wave, built that QUBO. We ran out of steam at around 30 seams. BMW's vehicles have a larger number of seams, as you would expect. But then we thought, well, can we take some of the technology that we've built for our own supply chain and repurpose it? And this is a so-called random key optimization approach, where you map your real-world problem onto a hypercube. And then within this hypercube, you use any kind of optimizer. In this case, we use dual annealing to actually solve the problem. The beauty of doing that is that suddenly, especially for these routing problems, every update that you do to the problem fulfills the constraints. So you don't have to worry about constraints. It's all built in automatically. And by doing this, we're able to solve the problem at scale and actually reduce the time to solve the problem for BMW by about 10%. And if you now think about the volume of vehicles that they make on a daily basis, 10% is a very large number. The next one was a POC done by the Volkswagen group, the binary paint shop problem. It's assume you have a production line, you have random orders coming in, you have cars that are painted in different colors, in this case, 2 colors. And of course, the goal is to switch the paint around as little as possible. So if you look, the center row of cars has 3 paint switches, the bottom row has only 2. And so just by tweaking the orders ever so slightly, you can reduce the overhead that it takes to replace the paint. Now we did a POC using QAOA on IonQ for a very small number of vehicles. But then once we had this mathematical formulation, we can just run it on graph neural networks and even scale it up to 1 million variables in minutes. And so you see, right, on one hand, we looked at what can a quantum device do for this problem, and we compared it against something that raises the bar very high. Because at the end of the day, we're building these machines to do something that we cannot do today, right? So again, here, the innovation was taking this physics Hamiltonian and then using graph neural networks to solve it at scale. The next one I want to talk about is actually kind of cool. This is options pricing. And when you think about options pricing, it is one of the workloads in the cloud that uses the most amount of CPU. And the reason is that traditionally, to solve the stochastic differential equations, you actually need to use Monte Carlo because they're very hard to integrate. So you approximate them. And Monte Carlo converges relatively slowly. If you do n runs, the convergence rate is just 1 over square root of n. So pretty darn slow for the error. And so what we discovered here, and this is 2 of my team members, Nicola and Michael, is that on one hand, we can do a end-to-end pipeline using quantum amplitude estimation. So if we had a scalable fault-tolerant machine, how many resources would we need? But on the other hand, we use tensor networks that are commonplace in the study of quantum systems and repurpose these to actually solve these differential equations at scale. And the results are quite surprising. For example, in the case of black holes, which is, granted, I give you that as the easiest possible problem you could think of, we had about 1,000,000-fold speed up over traditional Monte Carlo methods. And this can be adjusted to other types of differential equations as well. So in other words, you see, here we did something very different. We used a tool that physicists like to use to study quantum systems and repurposed it to study industrial systems or industrial problems. Next one I want to talk about is fraud detection. If you think about how fraud detection is done today, basically, you have tabulated data, you run some sort of machine learning algorithm over it, you do some sort of scoring, and then you say, okay, this guy is fraudulent and this one is not. What we decided to do is look at it through a graph-based approach. You can always cluster your transactions. So for example, if I typically show at Whole Foods and Amazon.com, and suddenly I'm buying flowers in Europe, then something's fishy. And so by looking at this graph structure, you can detect if there's outliers, and then by using a scoring algorithm, detect those. So we first did a hybrid POC using D-Wave. The only drawback here is that you need to take a problem that has Q colors and map it to something binary, so there is an additional overhead. But once we have this representation, again, we can use graph neural networks, analyze networks with billions of nodes. And so you see now we have a mathematical form that can run on a quantum machine, but again, we're solving it at scale today. Now the last result I want to talk about is portfolio optimization with quantum interior point methods. And here the goal was really to perform an end-to-end resource estimate such that we can see how many resources would we need if we use second-order cone programming to do portfolio optimization on a quantum machine. And the important thing here is that we really looked in detail at all the subroutines that have to happen, including block encoding of matrices, data ingestion, manipulation, et cetera, and then summed all of this up to do a very comprehensive study that basically gives us a good idea of how difficult it would be. And so we constructed these quantum circuits, but also did a paper and pencil classical resource analysis. So with this, I'd like to come to the end. It's, I would say, time to explore quantum solutions. If we want to build these machines, we need to know where they're going to have an impact. We need to understand where this technology will bring value. What problems will a quantum machine be able to solve? But we also need to build a community and do co-creation. I'm not an expert in finance, so we need to work closely with folks that are experts in finance, same for manufacturing, other areas. Or, for example, launch crowd science challenges. And the goal from us, from the Quantum Solutions Lab, is to build this portfolio of use cases so that we know then where we can leverage a quantum machine in the future, yet at the same time not really trying to make a hype out of it. If classical is the best way, let's stick to it. If quantum it is, we move to quantum. And with this, thank you for your attention.
Thank you, Helmut. We actually have 5 minutes left, so plenty of time for questions. So any questions, please? I'll bring the mic around.
Hi, thank you very much for your presentation. Could you go back to the slide when you talked about using tensor networks here? So could you elaborate a bit on how you solve the differential equation using tensor network? Because I understand that this is different from quantum Monte Carlo, right? So you're not doing that. Instead, you are using the tensor network to integrate the differential equation. How does that work?
That would take me more than 5 minutes to explain, to be very honest with you. The point here is, don't think about the word quantum for a moment. Just think about the fact that we have developed this whole tensor machinery, tensor contraction, tensor trains, et cetera, to be able to deal with these very high-dimensional spaces. And in the case of options pricing, you have multiple stochastic differential equations that have coupled noise terms. And so the idea really is to approximate the solution to these differential equations via not Monte Carlo, but basically a Fourier transform. And the advantage of that is that once you have all the k vectors, you can compute all the moments, your Greeks, et cetera, et cetera. So in some sense, it gives you advantages over other approaches. It might not be as precise, but it gives you a richer data set at the end with just one simulation.
So how is this quantum-inspired tensor network? Okay, thank you.
Feel free to reach out to me later. I can talk to you both about it.
Any other questions, please?
Oh, there's one right here.
Oh, I'm sorry.
After spending the last couple of years at a couple different places, thinking about these problems, moving fluidly between different forms of mathematics and them into the quantum realm back, what are the sort of one or two key lessons that you've really taken away that's just now inherent in every way you think about these problems? Might be more than 5 minutes too.
It might be. I would say let me put it this way, from a quantum standpoint, I think the first high-value applications will be in chemistry and material science. There's no question about that. Because you see, a quantum computer is a machine developed to simulate physics or chemistry. And so from that standpoint, it's pretty clear to us that once we have fault-tolerant chips, the value will really be in the areas of chemistry. On the flip side, as I said before, any kind of vehicle routing problem is just not going to happen at scale. I've seen the mathematical equations that, for example, Amazon Middle Mile uses for their use cases, and I can tell you that it's several pages of math. There's no way you can build a cubo around that beast. It's just not possible. You see, and so from that standpoint, you might say, well, isn't Amazon really good at logistics? Why are they making this hardware? Well, it's actually AWS making the hardware. You see, we want to provide a new type of compute to you so that you can solve challenging problems. So long story short, there are certain use cases that are going to be very difficult unless we come up with something very clever, and others that will be a slam dunk, if that kind of answers your question. But, sorry, last one on this. It's absolutely mind-boggling to me how little the tools that we use in physics are known in industry. This whole machinery of things that we have to study physical systems. And so physicists need to talk more to other people that are not physicists.
And time for one last question.
Thank you. One question about the use cases that you presented, about the output. So is it about estimating what kind of quantum resources are going to be required in the future, or is this about solving the problems right now and bringing some kind of quantum advantage right now?
Well, calling it quantum advantage right now would be misleading, to be very honest with you, because no quantum device today can solve a problem, a real world problem at scale. At least I've yet to see that, to be honest. Our goal, as I said, is twofold. We want to give the customer an idea what it will take to solve this problem, a quantum machine. But at the same time, we also want to give back to the customer something of value. In other words, figure out a way how to solve it today in ways that were not thought of before. So it's always this dual track. And if you want to build a machine that is going to do something that classical compute cannot do, then let's make sure that we raise the bar on classical high enough so that not some smart physicist comes down the road and says, haha, I found a new algorithm.